Okay, so what I'm gonna do is, well, I'll talk about this opportunity minus Laplacian plus V. V's, I don't know if you will enjoy it, but if you ever plan to perturb your operator with that kind of potential, which is a short range potential, then this might actually need something that will be useful to you. Because I'm gonna kind of also give another method of finding an agricultural expansion, so it will be another way of driving a distorted Fourier transform. So
Wait, and short range, that indicates like 1/√t or?
So let me do this. Oh, it's something like this. So I will have 1/1 plus x squared. So 1. So it's a little faster than 1/x kind of thing.
Okay.
I mean, the way that I define it, because I also want it to be bounded and then indicated. So, so what is special about this perturbation is, of course, H is diagonally under this, and we know it's spectrum. So basically, we have the essential spectrum H, and we have point spectrum.
Okay, so this is in 1.
Oh, this is in general RD. So the essential spectrum is 0 to infinity, and I have some point spectrum which are negative real numbers. So in particular, this essential spectrum is also equal to its absolute continuous spectrum. So what I have is, here is absolute continuous spectrum, and I have some points here. And in fact, I keep dropping over this. And in fact, what I'm gonna do is I'm gonna focus on this part. So mainly, if I look at the unitary operator, e to the I T H F, so this is gonna look like lambda J in the pure point spectrum, e to the I lambda J T E lambda J F, plus I will have a PAC H F, and I'm gonna focus on this part. So in order to focus this part, I need to define a resolvent operator. So I'm gonna define 2 resolvent operator. One of them is gonna be for the period of Laplacian. This is how I'm gonna define it. -1. This is Laplacian, not A. And
Yes. ACH, and then you
e to the ITH F. Sorry. So and then I'm gonna have our VZ, which is gonna be A finite Z inverse, and they're gonna be defined anywhere except the spectrum. So this is gonna define anywhere not in 0 to infinity, and this is gonna be defined. And Z is not so this is mainly what I'm wondering, of course, because I'm gonna go through the spectral measure. I want to understand what happens if I go from above and below to the real axis to my resolvent. So I want to understand how what happens to these guys. Do they somehow converge to some operator from as epsilon goes to 0? So that's what I want to check. And it turns out it does. So
and you want R0 or?
both R0 and RV, but I'm gonna start with R0 first, then I'm gonna extend it to RV. So so our first result is gonna be this. So as limit epsilon goes to 0, R0 lambda plus epsilon for I'm taking lambda positive. converges as an operator in weighted outer spaces, so it's gonna weight out to sigma to out to negative sigma. But if you ask what is this is just weighted out to spaces. So here I will have x to the sigma f to be out. Every time I write this Japanese bracket, but this Japanese bracket is this so it's just my hand keeps writing it, but it's just this. And in fact, the limit operator, which I'm gonna show it as this, as plus and minus are going to 0, lambda solves minus Laplacian minus lambda u equal f. So now I act with f in strong sense for f is out. So where does this come from? Well, I'm going to show it actually.
Sigma is
Oh yeah, sigma is greater than 1/2. So and this 1/2 is actually the best one. I mean, you cannot make it any better due to restriction, Fourier restriction lemma. So where does it come from is I'm gonna take the Fourier transform of all these. So this is gonna be a big representation of everything. Then you see, I am gonna of course do a little. I'm sorry. So I will have 0 lambda plus epsilon x inverse, and I'm gonna take my limits. Epsilon goes to 0. So now this is gonna be equal f c over c squared minus lambda minus epsilon as limits epsilon goes to 0. And now, either if you use like some kind of contour integral or it's just post-internal representation, then this is gonna look like f c principal value f c over c squared minus lambda. And you will have plus, I will have I pi over root lambda. Then I'm gonna have the Dirac operator where my radius is gonna be lambda, so C will be equal to lambda to the 1/2 times I will have FC for the transform. So this means, in fact, you see, if you look at the imaginary part, because this real part is fine, like its principal value. So the problem is the imaginary part. And if you look at the imaginary part, and if you take the inverse Fourier transform back, so remember I said that this is in the big sense, then in fact this is what you're gonna find. So if you look at the imaginary part of this guy, so the imaginary part of R0 lambda plus I epsilon f as limit epsilon goes to 0. So it's going to look like the inverse Fourier transform of this one. So I'm going to have first RD e to the I lambda omega x fx dx. Now I'm going to take the inverse Fourier transform, but omega is going to be in st minus 1. So I will have, sorry, this is going to be negative. I lambda, I have omega y omega, and what do I have? Pi, some constant, pi over lambda, and here I will lambda to d minus 1 because I have f Fourier transform lambda. Now you see, what is this? This is actually nothing but the surface measure of the unit sphere with radius lambda is convolving with f and divided by pi over lambda with sign constant. I think I'm gonna take off this because here's on everything. So you see what you have is basically first what you have, you take your f and then you restrict it in the sphere, and then you take it back inverse Fourier transform. So what you do is actually you just take your f and you just restrict Tf. So here you have the mapping L2 sigma to L2 where sigma is greater than 1/2. So this is the Fourier restriction, and now you take its adjoint. So you will find whatever that you're looking for here, and we go back up to sigma. So let's say I'm applying basically T star Tf if T is like a restriction of Fourier transform on the sphere with lambda radius. Oh, lambda to the 1/2. Right, lambda to the 1/2. Because I take lambda, usually I take lambda square, but because I didn't want to mess up with the spectral measure, so it's going to be all lambda to 1/2. This is going to be all 1/2. And yeah, I also have 1/2. Okay, so this basically tells you that now this guy that there is log-on, in fact, in the weak sense, maps L2 sigma to L2 negative sigma for any sigma is greater than 1/2. Right? So this is weak cat case, but I'm going to actually prove that this is also this works. This convergence is also true in the strong sense because he actually has another bound, which.
Sorry, what is T?
T, I just said it, T is the restriction of the Fourier transform on the sphere with radius lambda.
So T is you take the Fourier transform and then you restrict?
Yes, so it's here. So basically you just take the Fourier transform in lambda omega, where omega is actually in st minus 1. So we are actually over here, good. As I said, like I know I showed it in the weak sense, but it's actually also can be shown in the strong sense.
Sorry, what? So we're integrating the W as well, or omega?
Just these are W, which is in st minus 1.
Oh, we're integrating. Yeah.
Oh, sorry. I see. What's missing there? Anything missing? Clear. Okay. So in particular, actually, like I said, that this is this sigma 1/2 is the it's the optimal, and that's because in fact I can talk about by Bessel function expansion how the result is going to look like, and which is actually a form of an outgoing solution or incoming solution depending on the sign of lambda, right? So let's say if my f is some compactly supported function, which is I'm going to represent it like that, then actually I have a very nice formula. I know that how R0 lambda plus d minus lambda x is going to look like, at least when x goes to 0, like for large x. Let me write it here for large x. And if I say x is equal r times omega, so basically this is how it's going to look like. So I will have each of the plus and minus I lambda r over r to the d minus 1/2. Then you will have plus of I also have f lambda omega, again, these are 1/2, plus of 1 over r to the d plus 1 over 2. You see, this is exactly summer path radiation condition actually, because this clearly satisfies, if you look at that, this exactly satisfies because of this. We are plus and minus I lambda. If I call this U, U is equal 1 over R. So this outgoing solution basically gives you actually the summer path radiation condition. And I write it exactly like this, so that first you can see that you can now make this any better. And then later we will also, this is going to also play an important role.
Sorry, so I'm still looking at this. So is T this convolution? Or what's T?
T is the adjoint.
The adjoint of what?
The adjoint of the restriction. You take your F,
Okay.
you just restrict it on the sphere with radius lambda, and now you take its inverse back, right? So if you think it as the inner product, you actually have T, if you think this as restriction, and then T star is active, which is its adjoint. So you have T star argument, so you actually map out to sigma to L.
But it's, you take the transform and then you restrict.
Yeah,
And then the adjoint is you restrict and then you take the focus back and then the two restrictions.
And okay, sorry,
uh-huh.
I missed this notation. So what's L2 sigma?
Great.
So let me write it. So alpha sigma is x to the sigma f.
Okay.
Right? Is that good enough?
Yeah.
Okay, so I'm mapping from here to alpha, sorry, and then from here to its like the adjoint part. All right. Okay.
And you cannot do better than sigma 1/2 because the output, your output function will not decay faster than that. And
Yeah.
it is in L2 minus 1/2 minus. So
Yeah. So this is, of course, I have to say also something here, which is, this is in fact, I have to put a restriction of D is greater than equal 3, because in fact, you will see when I talk about the zero resonances, this formula is not actually valid anymore. So now we have the free resolvent, and now I'm going to talk about the perturbed resolvent. So in fact, what I'm going to do is I'm going to conclude the same thing for the perturbed resolvent. So in particular, I will have RV lambda plus and minus I epsilon is going to now converge in the same norm, converge as an operator to sigma to absolute sigma. And again, the limits, which I'm going to represent as RV plus and minus lambda, is going to solve this time H minus lambda U equal F, or F is in out. Okay, so did I miss anything? I'm going to say something. Of course, I need to say what is my B is, right? First of all, B is going to be, again, in the form of negative 1/2. So this is how my B is going to look like. And of course, I again have to say that lambda is greater than 0.
minus 1/2 for minus 1.
Minus 1/2, but yeah, that's always this form. This is equal 1 plus x squared.
Oh.
No, I said,
Did you find it?
okay, let's do this. Yes,
Now that I'm being the square root.
yes.
Okay.
Sorry, it's a little late. My brain is. Okay. So from now on, I fix it this way, and I'm not going to change it anymore. And now this is also the bound of my. I'm sorry.
And B is real.
Yes, it is real.
And bounded.
and bounded, yes.
I just-
to the same. Okay, so this story is over here. If you wanna actually talk about this convergence, you're gonna use the resolvent identity. So what do we have is we have RV plus R0 BRV is RV. So this is the second resolvent identity, but of course this is valid. Maybe I should say, first of all, when imaginary Z is positive, right? Then we're gonna take the limit. So in particular, when you wanna understand RV Z, what you wanna do is you wanna invert this operator. So you wanna invert this operator, and then once you can invert this, in fact, you can also talk about this RV. So if imaginary Z is positive, then this is gonna be invertible, because first of all, R0 B will be a compact operator. And you're gonna use the fact that this is compact operator, so you're gonna use the Fredholm alternative, saying that the singularities of this guy is gonna be isolated. So in other words, if R0 B is compact, then you have two choices. Either I plus RZB will be invertible, or so either this is gonna be invertible, or you will have a function, but because my imaginary Z is positive, this is the compact operator actually L2 to L2. So then that's why it's gonna be an L2 function, such that I plus R0 B F. So you have two choices because zeros are, I'm gonna use this one. I will write it again. But here, this is gonna be always the game actually, in x0 or whenever, which energy you're talking about. So if in particular, you have such an F, you see if I plus R0 B F is 0. In other words, if you can solve your F as negative R0 B, then this is gonna solve this F is gonna solve H minus Z U is equal to 0. So you see, if you just plug it here, you will see that it's gonna, I'm sorry, R0 B F. If F satisfies a condition like that, it's gonna always solve this. But this would mean that this guy is gonna have an eigenvalue, right? But because Z is not an eigenvalue for imaginary Z is positive, then F is gonna be positive. So that's always the game. Every time we check out either invertibility or not invertibility, and not invertibility is gonna actually cause an eigenvalue or some sort of a solution over here, which I don't really know the decay. If it's in L2, it's gonna be an eigenvalue. If it's not, then it's gonna be still solution. And then, so that's why it's gonna tell us that in fact, I am in the invertible case whenever my imaginary Z is positive. So now what I'm gonna do is I'm gonna go and take my limit as Z goes to real line. So in fact, I'm gonna check out.
So what is U? U means
I mean, this is gonna basically solve this. So basically, this is what you're gonna find if you just take out.
yeah. And so
You
then,
want, Is it clear? Or okay. So now, as Z goes to lambda, right? So as Z goes to lambda, now we have to be a little bit more careful because we know that now as I take my Z to lambda, then I will have lambda plus I epsilon will be RV I plus R0 lambda plus I epsilon V inverse R0 lambda. Now we know that as epsilon goes to 0, then I know that this operator, this time it's going to map L2 sigma to L2 negative sigma. And when I put this potential, this guy is going to be now compact operator, but it's going to be a compact operator from L2 sigma to L2 negative. So this time I'm going to ask actually the invertibility of this operator, right? Then I'm going to ask the invertibility of this operator. Are you invertible from L2 sigma to negative L2? So that's the question that we're going to ask. So it's going to be a little different because here we have an extra job. So in particular, either I'm going to be again invertible or I'm going to have a solution. I plus R0 lambda V F is going to be equal to 0. Either or I plus R0 lambda V will be invertible. So now if I'm here, if I'm invertible, I am good to go because that's what I was looking for. So if this is invertible, I take epsilon to 0. So this guy is going to be all good. And that's what I want to show. And so that's why I'm going to dispute the case that where there can be an F L2 sigma such that this is 0. So I have to dispute this case. But as I said, like the game was always, if I have such a solution, then I know that this F will be looking like R0 plus and minus lambda VF. And then this F will solve H minus lambda F0. So again, we have a 0 for my F. But this time, my F is in a form like this, which is, if you remember, it looks like an either incoming or outgoing solution. So it satisfies Sommerfeld radiation condition, right? So this is what we said, because by now V is going to have a decay, right? Then I can basically I can take my V and then take the Fourier transform of this guy. F has a, I just need to reduce F's decay at infinity. So this guy will be Fourier transformable, which I should say. Then I know that this is going to look like e to the plus and minus I lambda r over r to the d minus 1 over 2. Then I will have Bf Fourier transform lambda to the 1/2, I'm sorry, 1/2 omega plus O 1 over r to the d minus 1. So in particular, you see, Sommerfeld radiation condition tells you if you have a solution like this, which is I give you here the condition, and then this satisfies that condition. And if you solve this equation, then you have to be 0. So in particular, F is 0 due to Sommerfeld radiation condition. Because this is exactly the condition that Sommerfeld is asking for. And so in fact, my F is going to be 0. So I'm not going to be in this case. I will be in this case. So this guy is going to be invertible. Is this clear? Or it's missing something? So now this is invertible. And on the upper part, I'm invertible. So basically, I'm actually continuous, right? So, and then I can just, this guy is actually continuous invertible, not except everywhere. Because actually, I can say that I was going to say something else, but I don't really need because I use Sommerfeld radiation condition instead of another thing. So this means this guy is always invertible on the real line. So in fact, this operator exists as an operator to sigma to alpha negative in I call the limit as RV plus and minus lambda. And it is gonna solve. So in particular, that's the important part because the generalized eigenfunctions are gonna define from here. And in particular, I have that operator. And if F is in two sigma, and if I look at RV plus and minus lambda F, then this guy solves minus Laplacian plus F minus lambda squared U is equal to F.
Minus lambda.
Minus. Now, why did I need that, and why did I need everything in the strong science and everything? Because now, the way that Ikebe actually defined this for the first time, the generalized eigenfunctions, is going to have a form like this. You see, Ikebe says later this was actually exactly done by Agnew. We just changed the understanding a little bit. So they just look for a C function, actually maybe I should say C and X function, which is gonna look like e to the IXC, so my plane wave, plus VXC, where I would expect VXC to go to 0 in some sense, so that it will disappear at infinity and I will end up only here. And I want this to solve negative this Laplacian plus V minus lambda by CX equals 0. So in particular, I'm exactly looking for solutions over here, right? So I'm just perturbing my plane waves over here and I look for a solution like this. Now you see, what happens over here is, because I know that if minus Laplacian minus lambda, so this is going to be what? C squared, right? So now if this guy acts, that the minus Laplacian minus C squared is going to act on this, then it is going to give me 0. So in particular, I can solve my VXC, and that VXC is going to be solved exactly like RV C squared, and then I will have B. I'm going to start here e to the pi dot x cx. So this is how it's going to solve. Like this is how my VXC is going to come. And then this is okay now, because I know that actually this V is in the decay that I want, right? So I want V to be.
So you have a little V on the P.
Huh?
You have a little V on this capital.
This V, capital V, is the potential. This is the little V. Do you want me to change it to Q?
U is the solution.
W.
That was the normal back.
Angle anymore, so we're good with angle. So this is how I should define. And so in particular, this is how they define. And then my plan was actually talking about this in very detail. But honestly, because I was sick last week and I couldn't finish the paper. That was my original idea, to talk about the exact detail of that. But so basically what happens is, now once you have this WXC, then you can now define a distorted Fourier transform, and your Fourier transform is going to look like this. So basically you will have FF
at this stage, are you assuming that capital B decays
Yeah.
faster than, but so if it only decays like this, at least in some dimensions, then you will not be in L2 minus sigma, in L2 sigma.
Dimension is any dimension, is greater than 3. And
But so RV is really only defined on L2 sigma.
yes, I know. So that's why actually I told you that I needed to read this even in more detail, because actually everything starts with considering first a compactly supported function f, and then there's like a convergence such that they actually expand everything. And I couldn't get that part exactly. So that's why I'm just gonna mention about this part. I will give my Fourier transform and I will say that if you are interested, I will just read the whole paper and then present the rest of it next time. Yeah. And then I'm gonna actually define it, and then I'll give two properties and I go to the zero energies. So I exactly agree with your argument over here now. So hence this is how the distorted Fourier transform are defined for in general for any dimension for this kind of decay potential. So of course I will have some 1 over 2 pi d half RD, and I will have exactly this function. So I'm gonna have fx phi xc, and it's adjoint f is defined in a similar way. This kind of course, I will have fc phi xc. And in fact, what it satisfies is PACH F L2 is exactly equal the L2 norm of this guy. And further, if you look at PACH, and this is going to be also exactly equal, F star plus and minus acting on C squared F plus and minus F C. So in other words, it's really like diagonalize this H in the PAC. H. So this is
You have plus and minus that correspond to RV plus minus.
yeah. I mean they both. Do I have plus and minus here? Yeah, they both actually work.
And you can increase either.
So like in general, when they define the scattering operator, this is gonna be the coming wave, and then this is gonna be the outgoing one. This is in general how the scattering defines. So the paper also defines it this way, but the exact meaning for this, I am not able to really discuss. So and then what I thought is because you wanted to understand the Fourier, like this kind of distorted Fourier transform, the equation that you actually studied, if you look at on the PACH part, we can still maybe look for some kind of dispersion with this kind of equation. But I don't really know how things are done over here. So that's why I'm going to stop here, and then if you're interested, I will keep reading this paper, and then next time we can discuss in more detail.
And just to confirm, so the norm of F in L2, you can read it from the F plus.
No, plus and minus, yeah, plus and minus. They're going to be all plus and minus. They both are going to, because so I think yeah, they're going to be both plus and minus. Yes, it's like e to the IXC or e to the negative IXC. I think what they mean is you can actually define the Fourier transform one side and the inverse on the other side, or you can actually change it if you wanted to understand it.
But both of them work.
Yes.
So
That's what exactly Admont says. For B, that holds this.
you have two different Fourier transforms.
Yes. Distorted.
So basically, it depends on whether or not you want to fix the
Income and normal.
income, so you're fixing a plane wave at
Oh.
infinity, right?
Yeah.
And you're depending on whether or not it's the plane wave backwards in time or forwards in time, you get or you're doing something like.
I think it's not in time in general, but I think, and if you look at the like at the scattering poles, how they define I lambda r and negative I lambda r. So basically, either you are coming in or you are going out. I think that's how they define. So probably this is somehow sort of like the thing is gonna be also somehow related, because I don't know, maybe you're better. You have better knowledge. So
But okay, so I'm also confused about this. So you have H times pack H.
PACH.
Yeah. So that's an operator, right?
So yeah, so if like think about it exactly like minus Laplacian F.
Minus Laplacian. Oh, but I see. So this is the projection onto the absolute
Continuous spectrum.
of H. Okay.
Yeah.
I thought, sorry.
Yeah, so this is basically almost like a Fletcher-L on the absolute continuous spectrum, and then this is the fact that it's actually diagonalized.
So this is applied to F, right? This operator is being applied to F.
Yeah. Oh yeah. Yes. So this is actually, it's gonna come conjugate as well, like it's conjugate of that. I can check the paper actually on that. Okay, so here's my paper.
There, I think it's good that if you have the Plancheret, then you can just look at
They have both plus and minus.
So F scalar G should be equal to this F times this G, and then you just take the transpose. You get F scalar G is going to be F scalar transpose times this G, and so this way you can do it.
But the equation is really fill out the program in the past minutes.
So they're not exact conjugate, but they only have a difference of this imaginary part. So one is coming from here, like it's basically the difference in the Stone's formula. Yeah. So this is then to be continued next time. So but what I'm gonna do is next, I'm gonna talk about actually the lambda equals 0 energy. So basically you see, while all proving these, we all skip lambda. We said lambda is greater than 0, but in fact, lambda equals 0 affects very much the whole evolution. Like it actually determines how fast it decays. So now what I'm gonna do is, I'm gonna talk about these 0 energies, and I think that at the end of those we will be done. Okay, so clearly this is what we are looking for. So if my RV lambda plus and minus, and I just write an I plus R0 plus and minus lambda V inverse R0 plus and minus. So I'm gonna look at the invertibility of this operator at lambda equals 0. But actually there is a better operator, which is a symmetric resolvent identity. And then that's gonna help us more Because basically in that case, I don't really have to worry about L2 sigma, L2 negative sigma, but instead I'm just going to consider everything L2 to L2. And then that's because it's going to be symmetric. So I'm going to have V's on both sides. And this is how it's going to look like. So I'm going to, instead of this one, I'm actually going to look for R0 plus and minus lambda minus R0 plus and minus lambda V. And here I will have U plus. I'm going to explain what V's are in a bit. R0 plus and minus lambda V and V R0 plus and minus. So here, this little v is nothing but this. And then U is the sign of V. So it just applies this in the symmetric form. Now, because we have this, I'm going to only talk about L2 to L2 mapping. So the compactness from L2 to L2. So I want to try to invert this operator instead of this operator, which is that part. And then I want to, of course, understand this operator when lambda goes to 0. So what I need is all the expansions of this R0 lambda in terms of Bessel functions. So first I need to understand how they look like, and then I'm going to take my lambda to 0 to understand like how these thresholds are going to come over there. So in particular, as in the previous case, this is what we're going to do. I'm going to find a function that solves this, and then something related to that function is going to actually solve HQ equals 0. Where, of course, this time I have 0 instead of another eigenvalue, because that's where I'm trying to understand. Let's do that so that while I'm doing, it will be more. So now I'm going to look for how this guy is looking as lambda goes to 0. But as I said, in every dimension, my Bessel function's expansion is different. So in particular, first I'm going to start when dimension is greater than equal 3, because you will see when the dimension goes to 2 and 1, things are going to get a little different. So in particular, when you look at this operator, and if you take your lambda goes to 0, right? And lambda goes to 0, then this R0 plus and minus lambda has an expansion of this. So I will have, let me actually pull it as G0, which is the Green's kernel or Laplacian, plus I have lambda times, or maybe I should show it this way. I'm going to put O chi lambda. But what you should understand by this O chi lambda, I have to be careful. So I'm going to define this as an operator that maps L2 log to L2 col. So that when I put all those V's on both sides, I'm going to have a Hilbert-Schmidt operator. So now, if I look at U plus V R0 plus and minus lambda V, then this guy is going to be U plus V G0V. And then you see plus, I will have an Hilbert-Schmidt operator by lambda. So I'm lucky because now if I take my lambda to 0, that is the Hilbert-Schmidt operator, this is going to go to this guy. So in particular, at 0, it's invertible. He is exactly the invertibility of this operator. So which is a good thing, because I don't really have lambda singularity.
Great. So we really have two compactly supporting function. We would be something more detailed. Like so R0 plus and minus of lambda.
So I know that this maps to sigma to negative sigma. When I add these little v's with the right decay, right, then this is going to actually map L2 to L2.
No, it's just before, so G0.
G0, I didn't give the G0. Let me,
Oh, I thought G0 was a green function.
yeah, actually, G0 is this. Integral 1 over x minus y d minus 1 d. This is how G0 is exact. Okay, so what is wrong here?
So can you really say that R0 is this outside of the compact set? You're saying that the image of the arrow.
Not the compact delta book.
Yes.
Backwards. Okay. So does it map the range of Okai lambda?
Yo, this is L2 log to L2 prop.
The other way, right, the other way.
Oh, yeah. Yes. Sorry, yes. Yes, of course, yes. Sorry, yeah.
Also, it should be like some sort of lower order term, right? It should decay faster than the.
What?
So is the so G0 is just the inverse Laplacian.
Yeah.
And then the error term is gonna, do we know anything about like how that's gonna decay? If
Of course, it's gonna be
supported.
great. It's gonna be, in general, I know that this is gonna be alpha sigma to alpha negative sigma, so I will be fine. But the next guy is gonna be x minus 1 to the d minus 4. The minus 2 is already the Laplacian, the next is gonna be minus 2. So it's not gonna be any problem, right? So if you look at, no, basically this is what you are looking at. So you can basically look at dx, dy, x minus y to the d minus some decay, dy. So this is if you also have that. This is the operator actually you want to understand basically for the tail. And then you can always like bound this as a conversion operator. Right? Like the only thing that you need to increase is maybe the decay rate of the potential, but you will be always fine. Good. Continue. Are you still thinking anything about here, or this is good?
No, I think
Okay, because you were just looking over there, so I thought maybe there's something. You never know. So it's because sometimes I
I
put,
guess it was silver treat, but I guess once you put the weights, then you see that it should be silver treat.
yeah. Yes, that's actually that's why exactly why I write this in this form. Right? So that's why I use symmetric slope and identity, because over here things are gonna be a little more complicated than this. So in particular, if this is not invertible, then actually this is not invertible. Like if this is not invertible, it's 0, then this is not invertible, it's 0. So in particular, this is what I look for. Y equals 0. Similarly, again, either this is going to be invertible or it's going to have a solution, because again, I have this Schmidt operator, which is a compact operator. Then I can already use a further alternative. So either you have such phi, or you are not invertible. If you are not invertible, then you are good to go. But we are looking for if you are invertible, then you are good to go. But we are looking for when you are not invertible. So I'm actually looking for how these phi's are going to look like. So that's what I understand. So now if I solve my phi, that's going to look like negative u v g0 v phi. And again, it turns out that if you look at this guy, that's going to solve h minus lambda g0 v phi is equal to. Oh no, of course lambda is 0, right? I already made my lambdas. Yes. So so if I call actually this, let me call this phi, and now let's raise this phi. So I have 8 phi. So now the question is how this phi is gonna look like. And then that will actually tell me, do I either have an eigenvalue or do I have a resonance at 0? But you see, if you just look at this, in the kernel form, this is gonna look like b y, phi y, x minus y to the b minus 2. So when your y is large, then you have this b to compensate everything. So the only thing that you need to increase maybe the decay rate of b. But when x is large, then actually where you are having your decay at infinity, and then that determines if your phi is an eigenfunction or it's a resonance. I have the y here. So in particular, if you just look at, you just use like for x large, the Taylor expansion, then this is gonna look like 1 over x to the b minus 2, and then you will have b phi inner product plus, and you will have an alpha function. And then you see this is actually how exactly the resonances at 0 are gonna behave. So okay, we did it one side, but the other side is gonna take longer time. So in particular, if you have a resonance, it's gonna look like this, and then these are gonna be also the only resonances, right? So there is also if and only if statement, but I'm able to only show it one side. So in particular, this is what we have. So this will tell me if t is greater than 4, so you only have eigenvalue at 0. And if your d is either 4 or 3, then you have resonance function or eigenvalue. So because you see exactly, because this is only in L2 when d is greater than 4, whereas in 4 and 3, it's not in L2. It's in exactly L2 negative sigma. So and furthermore, you see if b phi is 0, then you only have OL2. So this is actually, I mentioned that because in general, when you look at the dispersive estimates, and if you want to find a faster decay, like there is a way that you can just take b phi to be 0, and then if there is a no eigenvalue, but not resonance, in general, you get a faster decay at infinity for the average. Okay. So now this is when dimension is greater than 4 and 3. It's greater than equal 3. But you see, last time you also discussed the two-dimensional version of the operator. So I don't know if you just maybe this will have some kind of understanding. I don't know. So now I'm going to talk about dimension 2. And then I might skip dimension 1 or so now if dimension is 2, then R0 plus and minus lambda is going to be is going to start with a logarithm term. So it's going to start with a logarithm singularity. So you will have something like c plus log lambda or some version of that, like some coefficient, like some multiple of that, and then you have the Green's function, and then you have finally similar or kind of some lambda 0 plus. I'm going to put because it's not exactly one. So and then if you just look at again u plus v r 0 plus and minus lambda v, then you have v lambda, you will have vv. Now you have vg0v, and then you have a conversion operator. So now I can narrowly take lambda to 0 because of this. But then what happens is this singularity is only in the space of v. So basically the singularity is in a space that is scanned by my little v. So what do? we just project it away from the V space, right? So I'm gonna call this space as my P, and I'm gonna project away from, meaning that I'm gonna write G lambda P, and I'm gonna write PQ space over here. So so I will have G lambda P plus, I will have, oh, I also have U, right? I forgot this somewhere here. I forgot to put this here. So I will have P U plus VG0 V Q, and I will have, wait, this is gonna go. Then I will have Q U plus VG0 V 3, and then I will have, I think I made a mistake over here, I'm gonna put that in a bit. V0 V. So I'm going with PQ. It's gonna go, right? Yes, this is what I'm gonna have. So now, then the first part formula has that if now this operator is invertible, then you can actually find and-
What is Q?
Huh?
Q is 1 minus.
Q is 1 minus, yeah. I actually also meant to say a lot of stuff, but that's okay. I think let's finish this and that will be done. So basically like invertible around 0 depends on this Q. Now, if I want now 0 to be an like if I want like this is not invertible as previous, right? So I need a solution to this guy. So in particular, I have a Q U plus VG0 V Q 5 is equal to 0. So now, if in fact, go ahead.
0 modulo something in the
Say it again.
so it's 0 modulo something in like what we use in
Yes. So that's only the resonance part. So this is gonna only correspond to resonance. Here you still have other resonances. So basically in 2 dimensions, that's why you don't only have one type of resonance, but you have 2 types of resonance. And one of them is gonna be this, which is only a constant. So in particular, like if I solve this, then I'm gonna have phi is equal Q V. Let me write that Q U plus V G0 V phi, right? Because phi is in Q. I'm trying to understand the invertibility of this in the Q space. So this is gonna be looking like minus P minus 1. I think I solved it wrong. Let me fix that. So I'm trying to understand how phi is gonna look like. So I will have U is gonna look like right. So I'm gonna put everything Q. What happened?
Q or Q.
Okay, so my brain is for plus this is gonna turn back to 5. Right. I need to have a constant, but right now I cannot see. So just a second. What happened here?
And if you just put the P on the other side.
So I will have 5 times P U plus G0 V phi minus V G0 V5 U. This is how it's supposed to come. U. Huh? Right?
You should get the letters. But you see that it's fine.
U squared is 1, yes.
Yeah.
Yeah. So in particular, this is a projection. So this is gonna be as P, which is, if I write it as a kernel, right? So I'm gonna write it as a kernel here. So I will have VV. It's gonna look like this, okay? So U, P is projection on VV. So I will have U plus VG0 V5. And I will have negative UV G0 V5. So if I take now, as in the previous UV out, right? Because it was coming from this side, then I will have V with inner product of U plus VG0 V5 minus G0 V5. Okay, and this is how my C is gonna look like. Okay, just I'm gonna look at it as well. And then you tell me if you see any mistake over here. Right? Because the P, I define it as projection on VV. So all I did is I put my P and then I took this UV out. So you see this is gonna be almost like the inner product. And then, so which is gonna give me a constant. And this is gonna be exactly this G0, which is gonna come from the Green's function. Yes? Good. All right. So in particular, my phi is gonna look like C0 minus integral logarithm x minus y, Vy, Cy, dy. So this is how it's done. And you see, this is gonna be in fact in L infinity. So in 2 dimension, my resonance starts with an L infinity, and that's because of the C0. And even though this looks like worse than L infinity, actually it is not, because my C is perpendicular to V, right? I took my C in the space of Q. So in fact, this guy is gonna look like, I can just write it as some logarithm x minus y over y squared Vy f. What do I have? Oh, I already have Vy dy. And then again, if I use, I'm sorry, this is gonna be x, because I'm able to subtract my x, right? So because V phi is perpendicular, V and phi are perpendicular to each other. In particular, I will have an infinity function here. And here, again, if I consider when x is large, you will have, and then expand like a Taylor for large x, you will have plus some 1 over x function. And then I'm going to put some constant here. And plus, you will have, again, OL2 in L2. So in particular, you will have a constant, which is an L infinity. I'm going to put C. So this is in L infinity. This is in P4, and P is greater than 1. And this is L2. So you have 2 types of resonances. You have either S wave, this is what we call S wave resonance, and either you have P wave resonance or you have an O eigenvalues. So this is how dimension 2 works. And then dimension 1 is going to also have a singularity, but I'm not going to make the story even longer. But if you look at dimension 1, then your result is going to look like 1 over lambda plus the Green's function. Then again, you will have a C0, L infinity S-wave resonance, but then you will not really have this part. And because you know that in one dimension you only have resonance, you cannot really have eigenvalues with zeros. That's the reason for that. So that was it.
You very tough one over X, we get going up a little bit better, like 1 over X squared. Due to the orthogonality.
No, you really have this guy. Look at that orthogonality, when you have an orthogonality, can you only have an eigenvalue? Is this the question?
No, the question is whether like you extracted the done asymptotic, and the question is whether you actually is the next term after the constant 1 over X or 1 over X squared?
No, it's for sure 1 over X.
And you can make it explicit.
Yeah,
Like,
yeah.
yes, it's,
Here you have
a product of psi and V times.
one polar. Oh,
But then you'll have the angle too, so you don't like a cosine.
no.
No?
That's good. Yeah.
Oh, actually, X squared is. Oh, yeah, I'm thinking that's one dimension, right? So because X squared is already in LP for P is greater than 1, right? You are right, I think.
No, I'm not sure.
Let's expand this, right? So because this is how where it is gonna come. So because we're just talking about for large X.
If you expand X minus y, you're going to have 1 minus 2 inner product of X and Y over X squared. And so I think your log, no, just the formula above. There is one for missing.
This is something is missing here.
Yeah, so there's the angle, so this
X
is
squared
true of
Y.
X and Y that are orthogonal, but generally you'll have basically. A cosine theta term where theta is the angle between X and Y. That'll give you your 1 over X.
I feel saying. I don't know. Right now I'm really my brain is frozen. Really it's actually frozen an hour ago, so that's why. So, but you are right.
But so then just have this, it will be in LP, P greater than 2. So this is a
Then this is gonna be P is greater than 1. That's for sure what it is gonna have. So let's expand.
Otherwise it would be in L2.
Huh?
Otherwise it would be in your big O of L2.
Yes, it's gonna be 1 over X then, right? If it's
So which is in P greater than 2.
oh, okay. Now I understand. This is what you mean. No.
No,
No.
we're-
So 1 over X is in LP for P.
Yeah.
Strictly larger than 2.
Yes, so that's
the right, because it's expansion.
yes.
Then this is good.
Yeah.
No,
It's okay.
Yeah, already right. So let me give you some time so that I will breathe first. Okay, so 1 over X squared negative 2. So with this, this is not in, oh, this is not, no, at infinity, this is not in L1, no?
Not in L1, it's not in L2 either. It's in L2 plus. Like anything larger than 2.
it's 2.1.
Then it's gonna be like this.
No, otherwise it would be in the big O of L2.
Then I'm really right now, I cannot really think, so I'm sorry, so just.
So that's good. Maybe we should do a long drive now. So that's good.
Thank you. So like the end part is absorption. But, so sorry about this.
Okay. All right, well. That's for today. That we, does anybody volunteer to write at least, talk about the, for you transform